Well, yeah, so let's do Q&A now. And let me see. So who would like to go first? Again, guys, raise your hands if you have a question. Oh, okay. Will, would you like to go?
Yes, the EmDrive showed that the end plate was superconducting. Does it matter if the whole EmDrive is superconducting, or you just want the end plate only to be superconducting?
Okay, that is a very good question, and one that I can't answer in any great detail, but I can tell you that different designs have been built and tested. And of course, if you have a completely superconducting cavity, then it works the best, but it is the most difficult to produce. Putting IPCO coatings onto curved surfaces is a very specialized business. It has been done, and it does give you the best performance. One of the probably better ways to go for early work is to take the flight thruster geometry, where you have actually two, you have a flat small end plate, and you have a flat central section of the big end plate. So you do in fact get quite a good superconducting performance out of that. Just to let you know that the early one that we did, the first superconducting thruster was built entirely out of flat flat elements, which was not easy to do, but it did work, and we were able to do a full super.
Okay, it looks like, again, these might be the bandwidth issues that Roger had mentioned having. That's why we had to do the video. Yeah, and he disappeared. Okay, he will be back in just a moment. It looks like he dropped off. Okay, let me see. So in the meantime, does anybody, I think—
Can we crank up the audio?
I'm sorry, John, the audio was too low for you?
Can we crank up the audio? I can hardly hear.
You might look at your speakers. Take a look at your speakers and see if you can get them on theirs.
Roger, maybe.
Actually,
I got a Bluetooth here, but I don't know how to connect it.
Okay. I'm gonna mute him out. Let me see. Sorry, Roger is back. Roger.
Yeah, I lost you momentarily there.
Oh, no worries, no worries.
It's a long way across the Atlantic.
I'm sorry. Where were you at again, sir? You had more to add, I believe, right?
Not really. It's just that there are a variety of ways you can build a superconducting thruster, and it doesn't always have to be totally superconducting.
Okay. Well,
I'll leave it at that.
let me go to Michael Boyd then. I will ask him to unmute, sir.
Hello, can you hear me?
Welcome back, Michael. I can hear you wonderfully.
Yes, certainly. Yeah.
Okay, so I have some general questions. When I got up this morning and I put my coffee, my cup in the microwave oven, and it warmed up real nice. In some of your presentation there, you were showing vehicles and stuff where there would be people near these let us say RF sources. I'm curious if you've considered any of the harmful effects of microwave radiation on biological entities like us.
Yes, again, a good question, but I've spent a large part of my career on high power microwave devices. And it is always a question you have to address. You know, you do not handle high power microwaves unless they are completely isolated, and you inevitably have checks. You have field meters around you to make sure that you don't expose anybody to microwave radiation. I mean, it is quite dangerous. You don't need many watts to give yourself a cataract or to blind yourself. And as you quite clearly mention, you know, if you have too high power and the typical microwave oven is only 750 watts, you can cook things. And so, yes, you do have to be extremely careful. Yeah.
Okay, so those are some of the challenges that you would have to address in commercializing the application of technology, is essentially what I'm hearing you say, correct? That's
absolutely
down the road.
but these are, you know, sort of, sorry.
That's
Yeah,
addressing
I mean,
that.
these are well.
Sorry.
Yeah, these sort of problems are well understood, and you know, we've handled high power microwave devices many times before.
So the other question I had also had to do with the yttrium, barium, copper oxide superconducting material that you were using. My understanding is they've found superconducting materials, higher temperature superconducting materials, and there is some evidence of using microwave radiation to achieve room temperature superconductivity. Have you considered any of those recent advancements in superconductivity?
Okay, I lost you again briefly.
Okay, no problem. I'll repeat. My question was essentially there's been some recent breakthroughs in superconductivity, other materials besides yttrium, barium, copper oxide, which is basically superconducting. My experience with it is it worked okay at liquid nitrogen temperatures, and I notice you're using liquid helium. But my understanding is they've made higher temperature superconductors now, and they've even developed techniques using microwave radiation to achieve room temperature superconductivity. Have you considered any of these new technologies?
Yes, certainly room temperature superconductivity is a target, and I'm aware of the work that's going on, some work that's going on there. But at the moment, the only thing that's in the public domain is actually using liquid hydrogen, not liquid helium. And the reason for liquid hydrogen is that once you've used the liquid hydrogen to cool the IPCO down, the boiled off hydrogen gas you can use in a fuel cell to produce the power. So it's there are, you know, clear advantages in liquid hydrogen, but as soon as room temperature superconductivity comes along, that'll be great. You know, it'll solve a lot of problems.
I'm just curious, what's the temperature of liquid hydrogen? I know helium, like what, 5 or 6 degrees Kelvin? What's hydrogen?
20 degrees.
20 degrees Kelvin.
20 degrees K.
Okay. Okay.
Yeah,
Thanks for all your
degrees.
answers. I appreciate it. That was helpful.
Yeah. And thank you, Michael. Okay, let me go to Benedek next. Sir?
Hi, can you hear me?
Yes, wonderful. Thank you for joining us, Benedek.
All right,
Yes.
so my question is about energy conservation. You need a lot of energy to go into orbit. And used energy is conserved in the EmDrive. And in the most ideal case, all the energy pumped into the cavity turns into kinetic energy. Now, where would a spacecraft store as much energy as needed? To get into low Earth orbit of 1 kilogram mass, you approximately need the energy of 8 kilograms of TNT. So how could you possibly store as much energy as needed?
Okay, let's do that in two parts. First of all, you cannot use all the stored energy in the cavity to produce kinetic energy. Otherwise, there's nothing left to produce thrust. So you need to keep a balance here. And typically you'd run a cavity at about, say, 50% efficiency. So you're turning half the stored energy in your cavity into kinetic energy. Now, the simple answer to your question is how you get things into orbit and how do you carry the energy? Well, first of all, you store the energy as liquid hydrogen.
Oh, and it looks like we may be losing Roger again. Yeah, Benedict, I did actually see your question earlier in chat. And so it is, thank you for asking that. And he should be back with us in just a moment.
Liquid hydrogen has more energy per weight than TNT, but I still don't think that there could be enough stored. So.
Well, I mean, I think you're making a very good point, right? When you're looking at the efficiency and stuff like that, then it does become a challenge. So I think you're asking some difficult questions about energy and energy storage and how you would use that. So it's good to ask that. It's good to address those questions, and hopefully that Roger will be right back with us. Okay, yeah, see, it looks like he may have to restart his connection here because it still lists him as being in the conference. And everybody, I should apologize to you for the challenges with our connection. Okay, it looks like he's dropping off and he should probably be back in just a sec. Jeremy, how are things going for you over in YouTube?
Good. Hey, you should probably have him do audio only if he's having trouble with the streaming, the upload, and the video, probably killing his bandwidth. So maybe when he comes back, we'll have him do audio only.
We'll try that. We'll try that. How
sure.
many folks do we have on our YouTube channel today?
Oh, it's quite a bit for Easter Saturday. 128, about 130.
Yeah.
Fluctuating. Cheers, everyone in the audience.
Well, and thank you for streaming us on Alien Scientist. Just as a reminder for everybody, Jeremy runs the Alien Scientist channel, 100,000 subscribers. He is doing, you're doing broadcasts all week long, right? I mean, you've done 3 or 4 this week.
I'm interviewing, I interview a couple different guests. I try to interview different people too. I'm trying to get people who come on your conference to also, cross platforms a little bit too. I interviewed you the other week too, so we could talk because you don't get enough airtime during the conferences. It's usually all our guests. So I gave you a chance to take the floor, and that was great too. So thank you for joining me for that. And we also do like a meeting with our engineering team. Probably like once a week we'll get together on a Zoom call all together and just discuss stuff live. And in addition to some other private chats that we engage in on the side, behind the conferences for the engineering side, for the actual lab side of this,
Okay, and it looks like Roger is actually coming back in. That's why I got, or he was attempting to. It looks like he's not back in quite yet. But yeah, no, that's good advice about the bandwidth. We'll see if he can stop his camera.
Yeah, we got a ton of new viewers from when I went on my friend's show, because he's my friend Ian is a regular on Tim Pool's podcast, which is a big show on YouTube, and I got a big viewership. It's like almost like going on Joe Rogan now that Joe Rogan's like not even on YouTube anymore, really. So that's cool. YouTube is kind of an interesting landscape lately. So I'm just I'm trying to rework a lot of my content to include more experiments from the team, and also more short videos and edited summaries, which I'm going to get into very shortly.
Ah, okay. And it looks like, yeah, so it looks like, again, Roger is back, but he's still having bandwidth issues. You know, some of this Wi-Fi connections cause a lot of trouble for folks too. Not as bad as it used to, but.
Yeah, I always recommend using a landline, you know, an Ethernet cable,
Yeah,
and plug in direct. That's like the best way to go.
Yeah,
I seem to have reconnected with you all now. Sorry about that. Sorry, you were talking about how you store the energy to get into orbit. Well, simply the energy is carried in the liquid hydrogen tanks, and if you do the calcs, and these are shown in some of the papers that I've written, you can see there's the sufficient energy to get you into orbit, albeit slowly.
Wonderful. Now, Roger, I am actually going, if you want to do it, I'm trying to stop your video. That may help your bandwidth. Jeremy Reese has suggested that. And I should apologize. I'm having trouble finding you. We got so many folks in today's conference. We got 44 people in the room with us. Oh,
so did you get that answer?
Yeah, oh yeah. Nope. I got the,
Good.
Yeah. There we go.
Yeah, I got the answer. I will quickly run a calculation. I don't think hydrogen is energy dense enough, and speed doesn't matter. So even if we discount air resistance, you need a fixed amount of energy to get into orbit, and for that energy, speed doesn't matter.
Yeah, and that's definitely something.
So,
oh, I'm sorry.
Yeah, can you hear me now?
Yeah, I can hear you now.
Yeah. If you can hear me now, yeah, you basically have to do the calculations of getting something into orbit, a mass into orbit, effectively going back to Newton's equations, and if you do that and do not try and solve it using the rocket equation, then you'll be able to come up with the correct energy requirements. I think the big problem is that everybody is used to using the rocket equation, and of course that doesn't apply to EmDrive. You don't have to carry the fuel with you, or you don't have to carry very much fuel with you, and because you're not throwing fuel out of the back of the rocket equation it just doesn't apply. You have to go back to basics and calculate the energy from simple Newton's equations and work from there. Try it, you know, I mean,
yes, that's what simple. I did.
Just try it out.
Yep. I just roughly have to go 8 kilometers a second. And that's the energy I calculated. I didn't even count the potential energy, gravitational potential energy. That's an additional over that 8 times TNT level.
Oh, okay. Well, Benedek, thank you. Let me go. Jeremy, do you have any questions in the YouTube channel?
Yeah, I have a question for Roger. What are your views on space-time, and what do you think space-time is?
Well, space-time is actually, as Einstein defined, it's essentially combining the 3 dimensions of space with the 4th dimension of time. Now, that's fine, you know, but it really doesn't apply to EmDrive. EmDrive is simple classic physics. You don't have to, well, not until you get towards very high velocities do you have to take into account special relativity. And at that point, you have to, correction that appears in the thrust equation, you have to take that into consideration then. So you'll never, for instance, get past the speed of light. And in fact, you'll get about 70% of the speed of light, and that's as fast as you'll get. But you know, it's up to these relativistic spacecraft velocities. It's really all Newton's laws.
All right, thanks. One more question is, what do you think? What are your thoughts on Martin Tajmar?
Yes. Well, I have to say that in October of 2017, I did explain to him why the NASA cavity was not going to ever give any thrust. And bless him, he spent 4 years proving that I was right. You know.
Good answer.
Yes. Jeremy, thank you, sir. Let me go to Plain C. Plain C, and that's, I believe that's a pseudonym. That is not hopefully not a real name. Where are you at, sir? Plain C had a couple of questions. I think he was asking about practical. Roger, if you're still with us, oops, so it looks like Roger might be, even without the video, he's still having bandwidth issues. So I wonder if that's a Wi-Fi problem. So we'll do Plain C next, and then Will Reichen had another question. And I should ask, are you guys all doing okay? I should apologize for some of the bumps on the road today.
Okay, did you get that answer?
Yes. Oh, and you're back. Wonderful. Thank you, Roger.
Okay, right.
I did.
Actually, it comes and goes.
Oh, no worries at all. I just appreciate your being with us. So we had another question. Plain C had asked. So he was wondering, I guess he was wondering about the next practical steps to test the concept. And he'd also asked about commercial space industry interest. Okay, it looks like Roger, are you still with us? Okay, and it looks like he dropped.
Yeah, I'm back again. The next steps. Well, I have to be careful here because there are clearly steps that have been taken that are not in the public domain. But if you move from what's in the public domain, then the next step is to fly first generation spacecraft, first generation EmDrive thrusters, and then fly small UAVs, small flying vehicles for second and third generation. That's the sort of sequence of things that will become known over the next few years.
Wonderful, thank you. Let me see. I believe actually Will Reichen had another question. Will. And then we'll go to, after that, we'll go to Gravity Alchemist. But it looks like Will's having.
Sorry, I had to find a question. My question is, you discussed the second generation and jumped to the third generation, where the third generation was a modulation. So my question is, are you looking at multimodal in the third generation? Is that a combination, or is that completely different physics?
Okay. The difference between the second and third generation is obviously a much quite a large increase in complexity. What it does give you is much higher acceleration whilst maintaining high levels of specific thrust. Now you can actually combine all three generations if you want to, but it's essentially the third generation is essentially, and the physics is still the same. It's just that you're employing, well, first of all, you're employing a well-recognized radar technique of using circular polarization to enable you to control the cavity length and also the frequency. And I have to admit, at this point, this was essentially a Chinese idea. I'm not going to say any more about that, but yeah, you know, but the physics is the same. There's no change in the physics.
If you're using AM modulation, then does that necessitate the cavity to be much larger than the microwave cavity?
Sorry, the AM modulation. I didn't quite get
the third generation. So so my question is, does that mean that you need a larger cavity for the? Yeah.
Yeah. Okay. I understand. No. The size of the cavity is really dependent on how much thrust you want to get out of it. So you tend to make cavities, the size of the cavity is dependent on the frequency, and so if you want very high thrust, you go down in frequency and higher and larger cavities. We've gone down to 500 megahertz cavities, and these are pretty big. But you know, like all in engineering, if you want to get a lot of power or thrust out of something, you inevitably have to go bigger. But again, it's not a question of whether it's first, second, or third generation. It's really how much thrust you want to get out of the beast.
Wonderful.
Okay,
Well,
so you're using the AM modulation so you can dump more energy into the cavity. Then essentially is what you're saying.
Yeah, the AM modulation is
are easier to handle. So
yeah, the AM modulation enables you to reset the if you like the cavity extension, and during the reset period you simply switch the power to a second cavity. So you do need two cavities in a third generation setup, and you're switching continuously from one to another.
thank you.
Thank you, Will. Okay, let me go to Gravity Alchemist next, sir. Okay, sorry about that.
I'm sorry. Okay, do you hear me now?
There we go. There we go.
I'm sorry about that. Hey, Roger, this is a great presentation. I really appreciate it. You've got some great nomenclature, and I'm gleaning a lot from all that information. I'm kind of new to science, so bear with me. I have a big curiosity. You had mentioned, one of my curiosities was same as the last question about how much thrust. I think you'd mentioned you tested one that has 720 millinewtons on about 2,000 watts of power. And I'm trying to correlate that into my little brain about what kind of SI unit that is. In other words, Is that something that's just scaled up in order to get the kind of thrust that's needed to move some of these large masses around? Can you elaborate a little bit on that, if you would?
Yeah, yes, certainly. The figures you quote are actually from Chinese work carried out at the Northwestern Polytechnical University by Professor Yang Zhuan and her group. And they are indeed the highest published specific thrusts. Not the highest specific thrust, they are the highest thrusts. Now these were done back in 2010, before everything went quiet for fairly obvious reasons. But essentially what you do is you scale up by increasing the Q of the cavity. So Professor Yang's cavity was pretty much like our flight cavity, around 50,000 Q. Now, if you go to a superconducting cavity, you go up by many orders of magnitude. I think the highest Q values people have got are probably about 5 times 10 to the 9 or even higher. So of course you multiply the specific thrust by that amount. You hit all sorts of problems, you know, like the Doppler shift due to acceleration. But again, it was the Chinese that actually contributed significantly to that solution. But you will not find in the public domain anything higher than those original Chinese results of 2010, and there's clearly obvious reasons for that, which I'm not going to go into.
Okay, well, all right. Super. Now, this Q that you're talking about, is the Q, how do you determine is there some kind of resonant, or you said you adjust the frequency in the cavity in order to get the maximum thrust out of it? Is there some kind of formula that I missed the first part of your presentation, I'm sorry, but in other words, the Q, it's based on the volume of the cavity and partly has to do with its shape. The other, you know, of course, but I was wondering why the speed of light changes at one end of the cavity also. You said 90, slower than 90% the speed of light at one end of the cavity.
Yeah, okay, let's sort of take each question at a time. The Q of the cavity is dependent on the dimensions, but primarily on the resistivity or the surface resistance of the material it's made of. So to go superconducting means you reduce the surface resistance inside the cavity by many orders of magnitude, you increase the Q. And all this is sort of, you know, standard formula out of microwave textbooks. Now your second question was, actually, what was your second question? It was, I know, it was to do with the speed.
Yes.
Yeah, it was to do with the speeds inside the cavity. Well, first of all, the speed of light doesn't change. I mean, you know, we're not changing C, but what we are changing is what's called the guide velocity, or sometimes it's called the group velocity. And this is actually the speed at which the energy and the momentum inside an electromagnetic wave is carried. Again, this is standard equations, you know, going way back to the 1950s. And you know, it's nothing mysterious about this. For instance, there's a well-known example of a very, very slow wave guide velocity. If you look at your microwave oven, you'll see inside the behind the glass window, there's a very small mesh, and the size of the holes in those mesh are designed so that actually the propagation velocity, the guide velocity, is zero. Otherwise, you'd fry. And you know, that's because in technical terms, the hole size ensures that you are working in cutoff conditions, and the traveling wave cannot travel through them. And again, this is all well defined in microwave theory. You know, it's why waveguides have to be a certain size to carry the particular frequency. So it's not the speed of light that changes, it is the guide velocity, which is always a fraction of the speed of light, depending on the size of the cavity.
Wonderful. Thank you, Roger. And thank you, Gravity Alchemist. So let me go next to Jacob Helvey, sir.
Hey, Roger, quick question here. So I'm just wondering if you've ever considered the effects of having more than one microwave source inside the cavity. Have you set that up in any of your designs?
Well, flight thrusters always should have redundancy built into their system. So yes, we have considered that for flight thrusters, it is not a bad idea to have two microwave sources. It's good old spacecraft engineering, building redundancy wherever you can.
Well, I guess maybe not so much redundancy, more so having two different opposing sources on opposite ends of the cavity. Maybe if you can play with the frequencies of each end, you might potentially see more thrust. I'm just wondering.
Not really, no. Your cavity is very carefully designed and sized for one particular frequency at the particular mode you've chosen to operate in. So bringing in another frequency source, it will not affect, really won't give you any advantage. In fact, it's definitely going to complicate the system. It's tricky enough getting the cavity to work with one source. You don't really want to bring in another at a different frequency.
Okay, thank you.
Yeah, thank you. Let me go back to Will Riken next. Will, go for it, sir.
Yes, you mentioned the Sapphire window and the YBCO, but what was the thickness on that? And also, does the thickness of the superconductor make a difference? And have you tried other superconductors other than YBCO?
Okay, the thickness of the actual superconducting film is not really that important as long as it's thicker than the skin depth that you need. Microwaves only travel very, very close to the surface of the conductor, and the thickness of the if you like the microwave currents, or the depth into which they go, is known as the skin depth of and this is always very, very small, measured in microns. What is important is to ensure that the substrate thickness, in this case it's sapphire, is thick enough to be robust enough to withstand the forces that you're applying as soon as you start putting power into these things. So you need some fairly thick substrates, but the actual thin films themselves are very thin, and as long as they're thicker than the skim depth, that's fine.
Wonderful, wonderful. Well, thank you again, Roger. Let me see. So we have time left. Does anybody else have questions? Mark, why don't you go ahead, sir?
I don't know if this was asked already because I did have to step out for a little bit, but have you read the paper that was in Popular Mechanics about Martin Tajmar's replication of your experiment from earlier this week? Do you have any comments on that?
Oh, actually, Jeremy asked
yes,
about that.
Okay, I'm sorry. I didn't. I'll check it then.
Well, if you want some more details, I can give you some more details, because the NASA cavity, which is the basis of Martin's work, and indeed at least 3 other organizations' work, is fatally flawed. It's a flat end plate cavity for a start, So if you do the simple geometry as shown in, I think it was slide 9, I think it was, you'll see that by the time you get to a Q of about 14, you've got a wave front phase error approaching half a wavelength. The whole thing collapses. You're never going to get the traveling waves in a flat end plate cavity. And there are many other problems he has. I mean, he claims a QU of 23,000, which is a nonsense. What he's doing is just measuring the Q of the input loop, because if you read the paper, you'll see that he uses a single port measurement technique. He claims a 45 dB return loss. That's not feasible when you're trying to balance a loop Q, a very high Q loop, and a very high Q cavity. By the time you get the impedance match correctly, we've never got more than about a return loss of 20 dB. So you know that the cavity that he's working with is not a traveling wave cavity. It's going to give you 0 thrust. 3 other competent organizations have also found this. And I advised one of them actually many years ago of all the reasons why a NASA cavity wouldn't work. And not saying it was my fault, but it wasn't long afterwards when NASA abandoned that work. So I mean, what Martin has done is put in a huge amount of effort into basically proving that the principles behind EmDrive are correct. Because if you don't follow the correct principles, you don't measure any thrust whatsoever. So I'm quite grateful to Martin, actually. I would never have done all that work myself, and I don't know of anybody else that would have put all that effort into it. So that's great, yeah.
Oh, sorry, Mark, I just muted. Did you have? Okay. Oh, Mark was just saying thank you, and I should say thank you as well. I should apologize, Roger. It's 2 o'clock. We're at the top of the hour, so I want to thank you again. Fine. Thank you so much for joining us, and everyone, please put your hands together. A giant thank you for Mr. Roger Shawyer. Roger, your work with the EmDrive is truly legendary, and I cannot thank you enough for joining us to present about it today. Okay.
Yeah, well, thank you for having me and for listening.
Thank you again, sir.